Hey everyone, and welcome back to another CTF Writeup video. So this was a very fun heap exploitation challenge, and it's kind of the standard heap exploitation challenge where you have a couple options to create, delete different heap chunks. But what made this challenge different is they don't give us a view chunk option. So normally that's how you get your info leak. You'll do some heap manipulation, and eventually you'll be able to see the contents, and there'll be a libc pointer there. So we don't have a view operation, and instead of having an edit operation, we have a add operation. And so the chunk sizes that we're able to create are OX18, so 24 bytes. And so we can specify 24 bytes and it'll add that to the current chunk contents. Just a little bit different. Unfortunately, I didn't solve this challenge. It was a pretty difficult challenge, and there were just so many other fun challenges. I worked on it for a couple of hours. I think I knew what the actual solve pattern looked like. I didn't get it through. So I solved the challenge afterwards, but I referred to some really great write-ups. One of them by Mymakin. Just amazing write-up. They go into a lot of detail talking about what they did, and they give their solve script. Highly recommend checking it out. Chovid also gave their solve script down here. Just great to see how other people solve the challenges. And so I referred to these a whole bunch while solving it after the CTF. But yeah, let's get started. So the challenge was called Math Door. It was part of Cyber Apocalypse 2023. We're given a Docker file and some download files. To kind of spill the beans about what we're going to do, the actual bug existed within the delete function, and I guess the delete allowed us to do a use after free because they weren't actually deleting the chunk. They would call free on it, but we could still edit the chunk. And so that use after free primitive, super powerful. Using that, we can do some kind of heap manipulation, some mangling, and we can overwrite the size of other chunks. I mean, we can do anything we want. And so I guess stepping back, our final goal is, since this was libc version 2.31, we still have the free hooks. And so the free hooks, we can execute arbitrary code as long as we put a pointer in there. And so once we know where the free hook is, we can put in a one gadget or a system or something like that, and we have easy exploitation. But like I said, there's no easy info leak. So we know what the end goal is. Eventually we want to write into free hook. We have our entry point, which is a use after free, and somehow we have to connect the dots. So to do that, there were two new vulnerability techniques new to me, which were very fun. The first is we're going to be using a unsorted bin chunk to leak libc. And so normally when you have a tcache bin, the pointers, when they're on the bin list, the chunk pointers will point kind of to each other. All the pointers stay within the heap section. But with the unsorted bin, the forward and backward pointers, if there's only one element, they'll point into libc. So that's great. So we'll have a libc pointer. Like I said, we can't view it though, which makes things fun. But we can still use it. That's all pretty much enough. The other advanced technique that we're going to be using is we're going to be mucking around in the file structure. All these processes, if you import libc, it's going to create a file structure for standard in, standard out, and standard error. And it's possible to do manipulation of those structures by modifying the flags and the write buffer to kind of reset the write buffer a little bit, such that on its next puts call or print call, it'll see that, oh, I have stuff I need to print, and it'll print all that stuff out. And so we're going to take that write buffer, we're going to say, like, actually write buffer, go back 100 bytes, because we can do that relative write. So we'll just subtract 100 bytes from the buffer. And next time it calls prints, it'll print a bunch of contents that are in libc, and obviously somewhere in there's going to be a libc leak. So using those two things, we'll print out an address. Then from there, we just create another chunk, and we can set that chunk all the way to the free hook, and then from there, we'll just write the system entry. But yeah, let's get started. There wasn't too much to reverse. We can look at reversing real quick. But first, let's just run the challenge. It was called Math Door. Here's our three operations: create, delete, and add value. So we created a new hieroglyph with index 0. So it's just a new chunk, size OX18. We can delete it. So I'm going to delete index 0. Cool. Like I said, there's that use after free. So now I'm going to do an edit. I'm going to edit chunk 0, and I'm going to add AAAA to it. You can specify up to OX18, so 24 bytes. And it'll just add each one of those bytes. So right now it's just adding the ASCII value of A, but obviously we're going to do this in Pwn tool, so we can specify a byte value of 1 or 0. That's pretty much it. We can take a look in Ghidra, but there really isn't anything too exciting. It's just going to iterate over and over. So there's this main function, it just constant loop. We have a couple of different options that we just saw, the math one, which is the add. There's also the create and the delete. we only get to create OX41 hieroglyphs, but it doesn't really matter. I think if we were to condense this, we probably would only need about 20. And like I said, when we do the delete call, we can see delete. It doesn't actually remove the pointer from this like global chunks array, so we're still able to call edit on it even though it's a free chunk. Yeah, that's pretty much it. From there, we can just jump right into the solve script. Starting out the solve script, it's not doing anything too exciting. Just standard pwn tools. We're going to load the binary. We set some context. Here are the 3 operations. So we can create, we can delete, and we can add. There's an add raw, because this one I specify integers, and this one I specify a byte stream. And then from there, we just start the exploit. So to cover the exploit again, because we're about to get into the weeds, and I think as long as you understand like the big ideas, it would be easy to reproduce this on another CTF. I think that's what's most important. So I'm going to cover the top level kind of overview again, and then I'll jump into GDB for those who are interested about, just like how to calculate different values, maybe some GDB tricks, I guess. But yeah, so top level, we're going to use that use after free to create some chunks. Then we're going to delete those chunks. We're going to put them on the tcache bin. And then since the tcache bin, they're going to have those pointers to previous chunks. What we're going to do is we're going to modify that so that it's kind of at an offset, so that when we create a new chunk, we're going to be able to edit the size of a different chunk. When we can edit the size of a different chunk, we can make that chunk large so that when we free it, the heap thinks that it's a unsorted bin chunk. Which is good because the unsorted chunks will have pointers to the libc arena. Cool. Once we have that, we're going to do the same operation 3 different times, where we're going to do some manipulation, create a new chunk that exists somewhere in libc. We're going to modify it, and we do that 3 times. And so the first modification we're going to do is the file structure. We're going to overwrite the file flags for standard out. Then we're going to create another chunk that points again in the file structure, but this time at the IO write buffer. So that we can set it back a couple 100 bytes, so that when next time it makes that print call, it's going to be like, oh, I need to print a bunch of bytes, and it'll print a bunch of bytes of random memory for us that'll have a libc leak. And then on the third operation, what we're going to do is we're going to modify the free hook, and we're going to set our system call there. So when we call free with a chunk that just says bin shell, it'll actually call system bin shell. Yeah. So starting from the top, step 1, we're going to use the use after free to create a misaligned chunk so that we can overwrite the size of a different chunk. Let's just take a look to see what it looks like now. So we're going to do pwn, gdb, attach, attach to the process. So we're going to create, delete. So nothing too exciting happening yet. We just want to make sure we're all on the same page. So I'm going to type, that was viz heap chunks. So we can see we have 3 chunks here. They all have size 21. And they all have 18 or OX18 bytes. So these different byte sections. So we freed 2 of them. And so this is the one that's not freed yet. And these are our 2 freed ones. And we can see that they have pointers. This one is pointing to 2AO, which is right here. So it's pointing to this one. And we can kind of also see that if we do bins. We can see this is the tcache bin. And we can see that it's pointing from here to here. So this value matches this value. This value should match this value. Cool. So that's where we are now. So now we're going to use that use after free, where we're going to kind of push the pointer. So instead of pointing to AO right here, we want to modify this size right here. So instead of pointing here, we want it to point here. So that's 2, 1, 2. So we need to add 30 hex so that it points here instead, and so that we can edit this value. And so the next step is doing that. So we're just going to, like I said, add 30 hex. To that first chunk. Then we're going to do a create, and at this point we should be able to modify that pointer and set the size so that we create a chunk of size 501. So let's see if that worked. Let's look at actually heap. Unfortunately, viz heap chunk is going to be a little bit weird because we have a big chunk. So instead I'm using this heap command, and we can just see all the different chunks we have. So this is that big one at the top that we didn't really look at. Here's a 21, and here we have a chunk of size OX501. So we're pretty good. We can look at this x, 100x at this address. Cool. So this is a heap chunk of 21, heap chunk of 21. We created a new chunk right here, and it has a size of 5, or we were able to overwrite the size of a different chunk. And so now that chunk has a size of 501 in hex. So bigger than what would go into the tcache bins. So we're hoping to get something in this unsorted bin. Cool. Let's jump down. So when we free a chunk and put it in a unsorted bin, it needs to point somewhere so it has that size. And so if you take the pointer for that chunk and you add its size, it needs to point to another kind of valid chunk. And I think it does that for like coalescing chunks, but that's easy to kind of get around. We can just create a whole bunch of chunks until it fills that size. And so somewhere down there's going to be another valid chunk. So we just create a whole bunch. So I do OX5, the chunk size, and then I divide it by the current size of the chunks. Each one is OX18 size, but bytes long, but then we also have the 8 bytes for the size. So it just works out. We just create a whole bunch of chunks. Cool. So once we delete the chunk, it'll go on the free bin. Actually, I'll just do it right here. So we're going to, oh, never mind. The exploit ran. So just kidding. We'll do it right here. We'll do, oops, not what I wanted. Go back. So we're here. So now if we run bins, we can see we have something in the unsorted bin, and it's at this address, and it points to the arena, which is exactly what we wanted. So let's look at this one. So again, this is our chunk that had size 501. And we can see instead of pointing somewhere else in the heap, like it would if it was on the T-cache, it actually points to a libc pointer, so that you can see that 7F. We can investigate it. I don't actually know what's there. It should just be somewhere in the arena, but we're gonna take that pointer. Yeah, so it's in the main arena. Cool. But now we have a libc link. We can't actually print it out, unfortunately. We don't have that print primitive. We still got to figure out the info leak, but it's good that we now have a chunk somewhere in here in the heap. We now have a libc leak, so we can start being clever with it. So at this point, we're going to do the same operation 3 times. Each one of these operations we're about to do 3 times. They all follow a similar pattern. We're going to do a delete, delete, delete. Then we're going to do an add, add, and then we're going to do a create, create, create. And what we're doing is, again, we're going to do that kind of pointer manipulation in the T-cache. And so we're going to free it. We're going to create a chunk by tricking what's actually on the in that bin list. And we're going to create chunks so that edit chunks so that they point into that libc pointer. And we're going to move that libc pointer around so that we can create chunks somewhere in libc. So the first one we want to create is one that points to a chunk so that we can overwrite this. So this is the standard out. So you can see what this looks like. Let's print it. So this is the flag structure for standard out. You can actually find this if you forget what this variable is. This is the address. If you just do print standard out, this is in our main elf section. So it's in the read write segment. So you can see it has an address of 56. Oops, VM map. So this is like loaded in, and it's in our variable section within the main math door elf. And so I'm guessing at some point during the linking and loading process, it'll be populated with the correct address in libc. So we have a pointer here that points to the actual file structure somewhere in libc. So I'm guessing it's right here. And what's fun, you can actually find it in the data section in the binaries. Would it be exports? Standard out? Yeah, so you can see we're going to use standard out. So we can see there's a pointer here for standard out. Eventually it gets filled out with the correct address that that starts with the 7F, but there's like a little holder for it already in our elf. Cool. So we have, like I said, we have this bin. It has the libc leak. We're going to try writing the flags. So this is that structure. We can then do file, and I think that's flags. And here are flags. Let's look at it in hex. So right now the flags for this file are OXFBAD2887. What we want to do is change it so that it'll start printing out contents. And again, I'm not an expert. I mean, I'm not even good at this stuff. This is the flags we eventually want. Instead of our OXFBAD2887, we want OXFBAD1800. I found this good article. There was an article I really liked. I couldn't find it though. That kind of goes over this like file system wrapping and all that stuff. I think it's file stream oriented programming, FSOP. But they talk about the flags here. So this is the magic number. This is what the base of the flags looks like. And we specifically want not IO no writes. We want IO currently putting and IO is appending. And so at the end, the bit set for that is FBAD1800. So we need to calculate the difference between what we currently have and what that is. Like I said, we're also, I guess I should actually go back a little bit. So we did delete, delete, delete. We created 3 chunks in the T-cache bin. We modified the very last one so that instead of pointing to instead of 8 would normally point to 7, but instead we're going to point 8 to our unsorted bin that has the libc leak. And so that way when we do create, it's going to point, instead it's going to create a chunk in the libc. We also need to move our libc pointer. Currently it's pointing somewhere in the arena, and we're going to point it so that instead it prints to standard file flags. So to calculate this value, really not too bad. Oops. We pretty much already had everything. So we want to put something at this address. So we just do print the address of this. So it's at this address. We also need our where the pointer currently is. So we can look at bins. It's currently pointing here. So we can just subtract the two. Which one's bigger? This one's bigger. We're going to say print this minus this. We get a value of 2752, which is what we have right here, 2752. So that's how you calculate that value. So everything's in place. Then we do create. Again, it's going to create that chunk. It's going to be at the flags. And then from there, we can modify our flags chunk ID with our new value. Cool. Then we're going to do that whole chain of operations again, except instead of overwriting the flags variable, we're going to overwrite the IO write base. So if we look back at our file, print, so there's all these different buffers. And so there's the read buffer, the write buffer, and I guess the buff base and buff end. But we're going to be looking at the IO write base, this one. And so I think we're writing that one. IO, yep. What we're going to do is we're going to set this back 100 bytes or so. And so the next time it makes a puts call, it's going to see that these don't match. And it's going to write everything from the write base up until where it's supposed to be. So we do the same sort of operations. We're going to do delete. Instead of pointing 12 at 11, we're going to point 12 so that it points to our libc leak in our unsorted bin. Then we're going to move the unsorted bin where it's currently pointing. Right now it's pointing at flags, but we need it to point at IO write base. This is only 20 up. But instead of writing 20, I was getting some error, and the challenge author, the solve script I saw was also hitting, I guess, the same error. It was easier if I just did OX10, so we go up 10 bytes. And so we can write 18 bytes. And so instead of writing the first one, we're going to write the first 8 bytes, we're going to write the last 8 bytes. So we're doing the same thing, we're just offsetting by 10. I'm guessing when we create a chunk over there, it's probably setting like some flag or something, like maybe the in-use flag or something, and it's something else is getting corrupted and upset. So instead we just move it up 10 instead of 20. To calculate these values, again, to calculate this OX10 and where the addresses are, very simple still. We're looking at P, right now the pointer is currently here. So this is flags, so we want the address of it, and we want to move that to IO write base. So you can just subtract these two. We can see it's 6C0 and 6A0, so that's how you get those two. So we create our chunks, we do all that stuff. I pushed it back 20 bytes. So when we push it back 20 bytes, we get a info leak, and I'll actually just show what that looks like. Where's our GDB? It's here. So we overset the flags, overwrote the flags, we moved back the write buffer, and we should have it here. So let's see what this looks like. Cool. It's a little messy because obviously the terminal is very large right now, but we can see normally it's printing out a whole bunch of garbage here, right here. And this is our leak. And so I saw if I only went back 20 bytes or whatever, we can see we have a libc leak right here. And you can see that 7F, 7F, B5, 17, blah, 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 blah. So it's pretty cool. Just by setting back that buffer, we can get a libc leak, which is crazy. It seems like a very powerful operation. And from there, this is the leak we got, and it's at a known offset from something else. I forget what it is. It is the IO21 standard in. Cool. So we can take that, and that's always going to be a known distance from the base of libc. So now we have our base of libc. Cool. And then the very last step, a nice easy step, we're going to do the same operation again, delete, add, create. This time we're going to point a chunk to the free hook, and then we're just going to write into the free hook pointer the system pointer. And we know what the system pointer is because we have a libc leak. We know where the free hook variable is. It's this print address free hook. Right now it's pointing, well, we should print it out. Right now it's null, but this is the address. And so we know where this is. Again, a constant offset. We're going to put a value in there. Yeah, we overwrite the value. We have to move currently our libc unsorted bin is pointing to the write base. And so we just need to calculate the distance between IO write base and free hook. I'll do it, but we pretty much already saw everything. So it's free hook. There's that address. Then we need this one, actually. Cool. And so we just need the difference between the two. Which one's bigger for this one? Copy, so we're going to print minus print. We can see it has a difference of 6024. Should be what I have. Oh, I have it in hex, so we can print out hex 1788. There was also that minus 10 up there, so we do need to account for the minus 10, which counts for the other difference. But now we got this value 1798, 17 again, that 1098. We move it up, we do create. So now we have a chunk that points into the free hook. We're going to write the value of system into the free hook. Right now it has a value of 0, so we're just going to print out lib sim system. And this works because we set the address of lib address up here, libc address, when we calculated the leak. And from there, we're just going to create a new chunk, add the value of bin shell into the chunk. And then when we delete it, it's going to call free. And so we're going to end up calling system free on bin shell, and everything just works. So what everything looks like, let's find GDB. Python 3, solve.py, ls, and we have shell. And we can run it on remote. I actually didn't run it on remote yet. Let's see if this works. We want, where do I create the process here? We're going to say p is equal to pwn remote. And we pray this works. Much slower on remote. It's creating all the chunks so the unsorted bin doesn't get unhappy. Hopefully we get an info leak soon. I think that might have been an info leak. And it worked. Cool. Cat flag.text. So the flag was your math is from another world. So overall, super cool attack. I think, yeah, the two new techniques for me were abusing the file structure so that we could leak a libc address, and then also just doing that unsorted bin attack. I knew it existed, I've just never done it before, and it was a lot of fun. So thanks to HB for putting together the CTF, and thanks to these amazing write-up authors who helped make sense of everything for me. So cheers. See you at the next challenge.